All right, guys, good morning. It looks like what we're going to do today is we did the virtual lecture on Thursday, which pretty much ran through the gamut of chapter 24. There's not a whole lot more to be said about chapter 24. Um, Chapters 23 and 24 lead into the next few chapters, 25 and 26, which are all about optics. And what will happen is in the previous chapter, we introduced the idea of electromagnetic waves, the idea that you have these disturbances that propagate through space. Well, light is an electromagnetic wave. What we perceive of as light is simply electric and magnetic fields oscillating around because electrons are wiggling around inside things. And when it comes to the understanding of light, there are actually two approaches that have been used in physics to deal with the mechanics of light. Originally, light was treated as a particle. The idea is that they're little tiny balls of light, if you will, that fly around and travel in largely straight lines. They bounce off of things and reflect. And that explains a lot of the properties of light pretty well. But there are some properties that don't work very well. And for those, we have to treat light like a wave, the way we did in chapter 24. So what happens is in the book, in chapters 25 and 26, it's going to follow the older sort of ray theory of light and treat light in one fashion. Then in chapter 27, the last chapter that we'll deal with in this class, that's where they shift gears and they go back and they treat light like a wave to investigate some of the properties that can only be investigated as a wave. And it turns out that light is in fact actually kind of both. It's both a particle and a wave at the same time. And so it has properties of both, and to understand you have to know both methods. But what we'll be doing in this next chapter is treating light in a very specific way before we change gears in chapter 27 to look at it from another lens. So in order for us to make this work, we have to introduce what we call the ray theory of light. We're going to treat light as a wave or as a ray, and we're going to follow the path of that light as it moves around. And there are certain behaviors that light will exhibit. Some of those behaviors have been long understood. Others were modeled, but they weren't really well understood until we understood the wave nature of light. And one of those we're going to talk about today. So let me do this. Let me switch over to a simulation so that I can talk to you about the ray theory of light and investigate one of its more important properties. I do not like this new design at all. All right. So what I have in this simulation is a laser that I can turn on, and it fires out a little red beam. So this laser is what we call a ray of light, and I can move it around and shine it in different directions, all kinds of cool things I can do with this little laser. Now, when we model a ray of light, we treat it as simply a simple beam that travels in a straight line until something makes that beam bend or bounce off of something. But understand that even though we're modeling light as a ray, it is still in fact a wave. And if you were to sort of think about what the wave properties of light might be, you can look at it this way. Right? This is the same beam of light, But here it's trying to sort of play up the wave character of the light. And so what you see are these little alternating bands of red and dark. And what those correspond to are the peaks and the troughs of the waveform as it moves through space. So if you were able to look at the side of this beam, what it would look like is you'd have the electric field, let's say, would be sinusoidal. It would be moving at the speed of light, which is pretty fast, to the right. And each of these right here would correspond to one of the red streaks in the diagram. And each of these right here would correspond to one of the black streaks. So what you're seeing is these peaks and valleys are moving away from the laser emitter at the speed of light. So bear in mind that even though we're treating it like a simple little beam, that beam has this wave-like character that we're just not centering on right now. Now, one of the things that has long been known about light is that when light enters a different medium, the light bends. So like right now I have the upper part of this simulation being air and the lower part of the simulation being also air. But what I'm going to do is I'm going to change the lower part of that simulation into water so that I have a beam of light going from the air into some water. And what you'll see happens is two things, right? This ray of light comes down, and when it hits the interface between the air and the water, the majority of the beam enters the water, but you'll notice it bends slightly, and it travels through the water at a different angle than the beam was traveling originally. There's also a portion of the beam that hits the water and instead bounces back off. So what we're going to do is we're going to call these two portions of my ray of light the reflected beam and the one that enters the water but bends is the refracted beam. And for the time being, we're gonna spend most of our time talking about the refracted beam. That's the more interesting one, and less on the reflected beam. You'll notice that I've got this little groovy intensity meter here, where it measures basically the brightness of the light, the intensity of the light. So out here, I have like a large, like all the light is there, so the intensity of the beam is 100%. However, if I sample the beam here, you'll notice like 92% of that light was refracted, and only the other 7.67% got reflected. So the vast majority of the light is being refracted in this case, and very little of it is being reflected. So it's probably worthwhile to ignore the reflected beam at first. Note, however, that percentage is not static. If I change my angle, you'll notice that a smaller intensity of my light was reflected and much more of it was refracted. If I make my angle a lot shallower, you'll notice, here 1/3 of the light got reflected and only 2/3 of it got refracted. So the intensity of those beams is going to end up being different depending on the angle at which I pursue this question. So let's center in on this refracted part and try to see if we can't make sense of this property of refraction, which happens basically all the time. To sort of make sense of this, it helps if I go back and look at it from the perspective of the wave point of view. Now, what's going to happen is if I take my laser beam and I'm going to move it so that it shines directly down, and I shine this down from air into water, you'll notice that here, the beam that enters the water, it doesn't bend, right? It just travels straight from the air into the water with no refraction at all. However, there is something a little bit different once the beam enters the water. To understand that, you have to realize that the speed of light that we talked about on Thursday, that 10 or 2.99 times 10 to the 8th meters per second, that's the speed of light in vacuum. It's the speed of light for light when it's traveling through empty space and not having to interact with any matter. However, since an electromagnetic wave is electric fields and magnetic fields, and because matter consists of positively charged protons and negatively charged electrons, when that light travels through some sort of material, it interacts with that material. And that interaction can get pretty complex. But the big thing that we want to understand right now is that when electromagnetic waves travel through any medium other than vacuum, it tends to slow them down. That 2.99 times 10 to the 8th meters per second, that's the high end of the velocities that are capable for electromagnetic waves. But in any other material, it'll be something slower than that. Now, granted, even in other materials, the speed of light is still going to be lightning fast, right? It's still crazy fast. It's just often considerably slower than it was in the other media. And you can see that that's what's happening here. Is my wave, if you look at the little red streaks, which are the peaks of those wave fronts, they're moving away from my laser at a constant speed. However, when my wave enters the water, the speed of light in water is slower than the speed of light in air. And so that first wave front, that first little red stripe that hits the water is going to slow down. However, when that first stripe slows down, the little stripe below it, the wave front behind it, hasn't hit the water yet. So it's going to take a brief moment for that second wave front to slow down. And so the guy in front slows down, the guy behind it doesn't for a second, and it catches up a little bit. And that's why you'll notice if you look at the wave fronts inside the water, if you look at this region in here, my stripes are a little bit closer together. The wavelength of my wave is a little bit shorter. So when traveling from a fast medium to a slow medium, the wavelength of my light tends to be compressed slightly. Neat. Now, the frequency of my light hasn't changed. If I were to stand up here and count how many wave fronts go past me every second, and I were to travel down here and count how many wave fronts go past me every second, those two numbers would be the same. So what's happening is the frequency is changing, or excuse me, the wavelength is changing, but the frequency is remaining unchanged. You can understand that process fairly straightforwardly if you remember that for every wave in existence, we could say that the velocity of the wave is equal to the frequency times the wavelength. And if I make this smaller, but I keep f the same, the only way the equation can stay true is that smaller. So if v gets smaller, lambda gets smaller, f is staying the same. That's what's happening when this beam strikes the interface. But look what happens if I have my beam strike the interface from a different angle than dead on, like this. It's really easy to see when I exaggerate it. So what's happening now is my beam is traveling down toward the water, but you can see that the bottom edge of my beam of light is going to hit the water a little bit before the upper edge of my light. So this stuff down here is going to slow down first, while the stuff that's still up here in the air is still traveling fast. And what that is doing is, since this part here is slowing down first, it allows this part of the wave to get further away, and it reorients the beam slightly. And so you can see that what's happening is this bending effect that we're getting when we go from air to water. It's happening because one edge of the beam slows down a little bit before the other edge of the beam, and that's causing the rotation effect. It's causing the reorientation. And now my beam of light is traveling in a slightly different direction than it was previously. So that's the big takeaway here, is that this property of refraction occurs because the speed of light changes from one medium to another. Anytime you go from two different media with different speeds, you're going to get this bending effect. You're going to get this refraction effect. Notice it could work backwards. Watch what happens if I change my scenario. So instead of going from air to water, I'm going from water into air. You'll notice that here I have the opposite effect. Here, my beam of light comes through here, but the left edge of my laser beam is going to start to speed up before the right edge of my laser beam, and that's what causes the bending effect. But also notice the direction of the bending is different. Here, when I have it speed up, it's bending further out this direction, whereas previously the bending was in the other direction. In one case, it bent more to the right. In the other case, it bent more to the left. So the direction of the bending is going to depend on whether I'm going from a fast medium to a slow medium, or a slow medium to a fast medium. And so what we need to be able to do is to quantify that process. So here's how we're going to do it. All right, I'm going to turn the ray thing on because it's easier to deal with. What we'll do is, when we talk about reflection and refraction, we're going to do this in terms of angles. And when we measure those angles, we're always going to measure those angles from the normal of the material, which in this simulation, the normal is indicated by this black dotted line, right? It's normal, meaning that it's 90 degrees with the interface. So here's the surface of the water. This is 90 degrees to the surface of the water. And what we can do is measure various angles relative to that spot. So the first angle that we're going to care about is something called the angle of incidence. And the angle of incidence is the angle at which the light hits the medium as measured from that normal. You can see the angle of incidence in this case because here's my beam of light. This right here is my angle of incidence. Now, when it comes out the other side and goes into the water, if I measure the angle between the normal and that second beam, that is what we call the angle of refraction. So again, this right here is the incident angle. And this right here is the refracted angle. All right. We could also, by the way, if we're going to deal with this reflected beam over here, we can measure this angle and call that the reflected angle. So the angle of incidence, the angle of refraction, and the angle of reflection. And so all we need to do now is to figure out what sort of math is going to underlie how those various angles interact with each other. Because clearly, as I move my laser around and change the angle of incidence, I will also be changing the angles of reflection or refraction very similarly. So for that, I need to shift my share so that I can draw. All right. So let's start off with the easy one first. Let's do that reflected angle. This is called the law of reflection. And the law of refraction is easy because it just says the angle of incidence is equal to the angle of reflection. If the beam of light comes in at 30 degrees, it's going to bounce away at 30 degrees. That was super easy. The law of refraction is a bit more complicated. This is called Snell's law, or the law of refraction. And the way this is going to work is the amount of bending we get is going to depend on how much the speed changes from one material to the next. And so that's going to depend on the particular material. Let's go back to that simulation for one more second. Because here, I took my laser from air into water. But you'll notice if I go from air into glass, I get a slightly different amount of bending. Here, I'm going to go from air into something wildly different. It bends even more. And here, I'm going to go from air into something wildly different. It bends less. So what's going to happen is the amount of bending you get will depend on the material. And so we're going to have to characterize every material by how much the speed of light changes when I enter that material. And so in order for us to do that, we need to introduce the concept of the index of refraction. So first we have what we call the index of refraction. And for any material, we will define the index of refraction as being the ratio of the speed of light that you get in vacuum, which this is what we call the letter C, divided by the speed of light in that material. Now, in vacuum, the speed of light C is that 2.99 times 10 to the 8th meters per second. That's super easy. Here, this is the speed of light in whatever my new material is. And here's the deal. Any material that you're talking about, the speed of light in that material can never be larger than the speed of light in vacuum. This is the fastest that literally anything in the universe can ever go. Nothing can ever go faster than this. So this V here is at best going to be the same as this. At worst, it's going to be slower than this, which means this index of refraction cannot go lower than 1, right? The index of refraction must always be at least 1 but more than likely it'll be larger than 1 because I'll be dividing by a smaller number than I have up top. So most indices of refraction will tend to be numbers that are larger than 1. Now, you're not going to have to memorize any of those with one exception. Obviously, the index of refraction of vacuum is by definition 1 because that would be C over C. And air doesn't slow light down very much at all. The index of refraction of light ends up being like 1.0024, which is close enough to 1 that we usually treat air or vacuum as having an index of refraction of 1. So you should certainly know that air has an index of refraction of 1, but other materials will be larger than 1. Now, we were just dealing with the simulation a moment ago. We were going from air into water. And it turns out that for water, the index of refraction is about 1.33. For glass, and of course it depends on the type of glass, N is somewhere in the neighborhood of about 1.5. Right. Notice if you know the index of refraction, if you know what N is, you can figure out the speed of light in that material. So, just for grins, if I'm looking at water and I want to know what the speed of light is, well, since N equals C over V, that means that V equals C over N. So if I take 2.99 times 10 to the 8th, and I divide it by 1.33, that's going to tell me the light in vacuum. So it's 2.25 times 10 to the 8th meters per second. Right, that's still blazingly fast, but it's a good deal slower than it is in air. So, how do I use this index of refraction to do the law of reflection? Well, Snell's law can now be written like this. So if I take the index of refraction of the material that I'm starting in times the sine of the angle of incidence, it will always be equal to the index of refraction of my new material times the sine of my angle of refraction. And so I can solve problems in that fashion. So in that simulation that we were just doing, we had a bunch of water, we had a ray, here's my normal, and let's say that my angle of incidence was 30 degrees, and I'm going from air into water. Well, what's going to happen is when I go to find theta r, well, I know that n1 sine theta I is equal to n2 times sine theta r. I'm going to be solving for the sine or for theta r, so I want to get n2 on the other side. And notice, by the way, that in this case, I'm going from air to water. So out here, N1 is equal to 1, and N2 is equal to 1.33. Anytime I'm going from places where the speed of light is large to where it's small, N1 is going to be a bigger or a smaller number than N2. So N1 over N2 is going to end up being a smaller than 1 number. That means that if I'm taking a smaller than 1 number times the sine of theta I, I'll be getting a smaller angle for theta r. So in general, and this can help you sort of reason your way through problems before you do the math. In general, if I'm going from a low index of refraction to a high index of refraction, you expect that your angle of refraction is going to be a smaller number than the angle of incidence. In other words, your light is going to bend to be closer to the normal rather than further away. If, however, you were to reverse the situation and go from water, where the speed of light is low, into air, where the speed of light is high, then it would be reversed. And what would happen is N1 would be larger than N2. So I'd be multiplying by a number bigger than 1 here. That would suggest that my angle for my refraction would be a larger angle than my angle of incidence. So if you're going from water into air, then what's going to happen is this light is going to bend further away from the normal. So going from fast to slow, it bends towards the normal. Going from slow to fast, it bends away from the normal. And just knowing that can sometimes help you reason your way through problems that otherwise would be a pain. So let's do this. I've got N1, which is 1 times the sine of 30 degrees. I'm dividing that by 1.33. Then I've got to take the inverse sine of all of that to get theta r. So take the sine of 30, divide that by 1.33 is 0.375. Take the inverse sine of that. I get 22 degrees. So according to our math, if I go from air to water with an angle of incidence of only 30 degrees, I'm going to come out in the water at a slightly smaller 22.1 degrees. All right, does that check out with our simulation? Let's go back and look. So I've got a little protractor here, and here's 0, so 30 degrees. And lo and behold, if you look, here's 0, there's 10, there's 20, yeah, 22 degrees. So far everything pretty well checks out here. And that's how the law of refraction, or Snell's law, works in practice. Now, you do get some kind of cool variations on that. One thing that is pretty neat is if I go from water into air. So here I'm sending my beam from water, where the index of refraction is 1.33, into air, where the index of refraction is 1.0. And you'll notice that out here, the angle of incidence is smaller than the angle of refraction, which is what we anticipated, right? My angle of incidence is still 30, but now what's going to happen is if I take 1.33 times the sine of 30, and then take the inverse sine of that, this should be about 41 degrees. So there's 30, there's 40, so 40 and change. Yep. So that works fine. But watch what happens as I make my angle of incidence get larger and larger and larger. So here I am, I'm going larger, 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 larger. Oh, wait. So out here, what's happening is I don't get any refracted beam at all, right? My light is inside the water, and when it tries to leave the water, it can't enter the air at all. And instead, all of the air, all of the laser, looking here, I have 100% here and 100% here. So literally all of my laser, when it tries to leave the water, instead it just reflects and remains inside the water. We call this process total internal reflection. And it occurs in situations where I'm going from a large index of refraction into a material with a lower index of refraction. We notice we didn't get that at any point. I'm going from air to water, no matter what I do, I'm always getting a reflected and a refracted beam. But when I switch it around and go from water into air, there are some angles at which I only get reflection, and it's only at other angles that I get refraction at all. So what gives with that? Why is it that I'm getting no refracted beam in this particular example? Well, you can kind of see it if you watch where it kicks in. Because look, here I am, I'm making my angle of incidence get larger and larger and larger. And the angle of refraction is also getting larger and larger and larger. But notice the angle of refraction is always bigger than my angle of incidence because I'm going from fast or from slow into fast moving media. And you'll notice that as I make this angle larger and larger, you see how this beam of light is getting, this angle is getting so big? At some point, what's going to happen is this angle is so big that it's approaching 90 degrees. And to sort of get a sense of why this is going to end up making my refracted beam go away, let's go back to the math for a second and think about what the math tells us. Wish there were a keyboard shortcut for going between those two different screen shares. That'd be super cool. So let's go back and let's think this through. And we'll see sort of what's happening. So Snell's law says N1 sine theta I equals N2 sine theta R. And we're going to be solving for the sine of theta R. So I'd get N2 on the other side. So N1 over N2 times the sine of theta I is equal to the sine of theta R. And so if I go to solve for theta R, I take the sine inverse of both sides. And to see why this plays out the way it is, you have to have a more intuitive sense of what the math that we just wrote means. So when we look at this sine inverse function, we've written this a gazillion times, but what does it mean when I do the sine inverse of something? So like if I put in my calculator, sine inverse of 0.5, right? What I'm asking my calculator is, hey, calculator, can you tell me, if this is theta, I'm basically saying, hey, calculator, what angle can I take the sine of and get this number, right? That's what the sine inverse means, is what could I take the sine of and get this ratio? And so obviously to get 0.5, you do 30 degrees, right? Because the sine of 30 equals 0.5. So when you're writing sine inverse of 0.5 equals something, you're asking the calculator, what could I take the sine of and get the number in the parentheses? Now, let's think this through here. Up here, we're saying, aha, what angle could I take the sine of and get this expression in parentheses? However, what do we know about the sine function? The sine function looks like this. And what's going to happen is the biggest the sine function ever gets is +1. The lowest it ever gets is -1. So what's going to happen is if N1 is bigger than N2, this is a number bigger than 1. And if this number bigger than 1 times the sine of my angle of incidence is still bigger than 1, then what's going to happen is I'm asking my calculator, hey, can you find me an angle that I could take the sine of and get 2, right? If this number in here was 2, what angle could I take the sine of and get 2? And your calculator is going to be like, look, dude, you can't ever get a number bigger than 1. So there's literally no solution for which you could take the sine of some angle and get 2. And so what's going to happen is total internal reflection is going to happen anytime this part in here exceeds 1. Does that make sense? Now, what if the thing in here exactly equaled 1, right? That would be the upper boundary, the biggest angle of incidence that you could possibly have when this gave me a sine of exactly 1. Well, what angle gives me a sine, or what angle, or the sine of what angle gives me 1? 90 degrees. So you can sort of see what's going to happen is, if you want to find where this total internal reflection is going to kick in, you got to figure out what angle of incidence would give me an angle of refraction of exactly 90 degrees, because anything more than that, you're going to have no solution. So that's how we'll solve the problem of total internal reflection. We'll go back to Snell's law. And if we want to find the biggest possible angle of incidence, what we'll do is we'll take the biggest possible angle of refraction, which in this case would be 90 degrees, and then solve for what theta I makes it work. So sine of 90 is 1. And so this right here is what we call the critical angle. For total internal reflection. And it's going to be the ratio of whatever N2 over N1 is. So in this case here, if I was doing from water into air, well, water is going to have an index of refraction of 1.33. Air is going to have an index of refraction of 1. So 1 divided by 1.33, take the inverse sine of that, and I get about 48.7 degrees. So going back to my simulation, having done the math, what this suggests here, here's 30, here's 40, here's 50, so we're approaching 50, and lo and behold, at about 47 degrees, anything beyond that, and none of the light escapes. I get no reflection or no refraction, and I only get reflection. So that's pretty neat. Now, why do we care? Big flippin' deal. Well, you may have seen some of this. If you've ever gone out like on a lake or something, and you look down in the water, there are sometimes limits to your visibility, like your ability to see inside the lake or even a pool is going to be somewhat limited. Because imagine that you're standing by the edge of that body of water and you're looking down at a fish or a swimmer or something below you. So here's the surface of the water, and maybe you're up on a dock or something and you're looking down. Right. If there's a fish swimming like right up near you, what's going to happen is, in order for you to see that fish, light from the fish is going to have to get to your eyes. Now, normally what would happen is if there were no water there, if there was no such thing as refraction, the light from the fish would go straight toward your eyes and you would see it. However, because the water is going to refract upon leaving and going into the air, this ray of light that's going straight from the fish towards you is never going to reach your eyes. It is instead going to go and it's going to bend, and I'm going from water into air, so it's going to bend away from the normal. And what that means is that fish, the light from that fish that would normally reach your eyes, is actually going to end up over here. So if somebody was standing, say, behind you, this person is going to see the fish. However, for them, what's going to happen is the light is coming from here. To them, it's going to seem like the fish is really a slightly different position from where it really is. Like, it's going to seem to them that the light came from this location and the fish is really here, when in fact the fish is there. Now, meanwhile, what about you? Well, for you, what's going to happen is there's going to be some light that leaves the fish that normally would have gone right past you. So it would have gone normally and never been seen by you. However, what's going to happen is this light is going to bend such that it hits your eyes. So what's going to happen is you will see the fish, but to you, it's going to seem like the fish is over here somewhere. Because that's where the beam of light is traveling to you. You're used to thinking about light traveling in a straight line. So when this light arrives at your eye, you're going to conclude that the position of the fish is along that same straight line, when in fact, it's having this surprise bend when it leaves the water. So the locations of objects that you see under the surface of the water are going to be exaggerated or more difficult than others. Notice, by the way, that the amount of bending you're going to get from this fish, because the fish is up next close to you, is going to be less bending than this person's going to see. So you're going to see the position of the fish change less drastically than this person would. And what about if there really is another fish way out here? Well, what's going to happen is for this fish, it's possible that the angle of incidence is so large that it experiences total internal reflection. None of the light leaves out at all, which means you can't see this fish at all. So fishes that are up here right underneath you, you're going to see them, but they're going to appear to be in a slightly different location than they really are. Fishes that are way over here, you can't see at all. So to you, looking out here, you're just going to see nothing but the surface of the water, whereas things that are right up next to you, you can maybe perceive objects under the surface of the water. And you've probably seen that in pools or lakes where you can see through the water near you in your immediate vicinity, but further out, you can't see into the water at all because all the light from underneath the water is experiencing total internal reflection and therefore doesn't arrive at you. Plus, heck, what if you're this fish over here? This fish over here is going to believe that this fish is right there because he's going to see the reflection of the fish off of that top surface. So that's one reason that you might care, is that it sometimes, does create weird optical situations. Sometimes if you ever have like a fish tank in your house and you look in the aquarium, you can actually see the interior walls of the fish tank sort of act like a mirror-like surface, because what's happening is light trying to leave the fish tank is experiencing total internal reflection. And so, if you look through the front of the fish tank and try to look out the side, you may not see out the side at all because of the reflection property. So the side of the fish tank may appear to be mirror-like from the interior. So that's pretty neat. There's other reasons why you might care. If you have fiber optic high-speed internet, you definitely care about this because this is how that high-speed internet signal gets to your house. So what a fiber optic cable does is it's like a long cylinder, and the interior of that fiber is made out of some clear material. And then what they do is they surround that fiber by an outside layer called the cladding. And so what you've got is two different materials. You got both of them are clear. The inner material, however, is going to have one index of refraction, and the outside layer is going to have a different index of refraction. And what we want to do is we want to have total internal reflection, which means the middle part, this interior part, have a large index of refraction. The cladding is going to have a smaller index of refraction. And then what happens is you shine light or pulses of light with a certain frequency into one end of the fiber. And so what's going to happen is, as long as the ray of light shines through at a shallow enough angle, when it gets to the edge and it tries to go from the inner part into the cladding, it experiences total internal reflection. And instead of entering the clear part here, it just reflects. But then when it gets down to here, it's coming away at the same angle it came in at here. It's going to bounce here as well. And so what's going to happen is you send rays of light, they just kind of bounce around on the inside, and the light is constrained to stay inside this thin cable. Then if you take that thin cable and you bend it around and turn it or lay it underground for miles and miles and miles and miles, you can send those little light signals on one end, and you'll get those same light signals come out the other end without any loss of signal. And of course, we encode these pulses of light in a binary code so that we can send computer information that way. So rather than sending the information in terms of electrical signals like you would during an Ethernet cable, you're instead using light to do it instead. And you can make this travel over very, very large distances by harnessing total internal reflection. You'll lose some fraction of your information because maybe some of your light came in at a super steep angle. It's going to refract and leave the cable, but the vast majority of it's going to come in at shallower angles and bounce around forever. And so that's how fiber optics work. And you can use that for all kinds of information technology needs. Pretty cool. So that's Snell's law. Now, obviously, there's going to be more to it than that. And in fact, the big reveal in chapter 25 is that you can make optical instruments with a clever application of Snell's law. Let's go back to that simulation again. And for this one, what I'm going to do is I'm going to go over to the prisms portion. So here's my handy dandy laser, and here's a big old piece of glass, and I can take that piece of glass and I can rotate it various which ways, and I can shine light through that glass. Now, if I shine it like here, what you can see is happening is here's my ray of light, here's my laser. Right now it's coming in here with an angle of incidence of basically 0 degrees because it's coming in directly toward the normal. Can I turn the normal on? Yeah. So now you can see, you actually can't see. So here's the normal, but right now the normal is in the same direction as my beam of light. So it's coming in at an angle of 0. It's going to refract at an angle of 0. So basically my light goes into the glass and does not bend. It goes all the way through the glass. Here it's going to hit it with an angle of 0 again and then not bend. And so here, when I shoot my light dead on, it just goes straight through the glass and out the other side with no bending to speak of. Yay, super awesome. However, if I rotate my glass like so, you can see that what's happening here is my ray of light is coming in. It's got a large angle of incidence. When it enters into the glass, it's bending towards the normal. So the angle of refraction is now smaller than my angle of incidence. But then that beam travels through the glass and is incident on the glass on the other side. And, you know, groovy little math thing here. This line here is parallel to this line here. So I have two parallel lines and a transversal. Alternating interior angles are congruent, which tells me that for this particular example, this angle here is the same as this angle here. So the angle of refraction on the left side is therefore the same as the angle of incidence on the right side. And of course, if I have this angle of incidence here, this angle of refraction here is going to end up being exactly the same as the angle of incidence here. So what will happen is my light comes in oriented one way, it comes out running parallel, but it's shifted. If the glass hadn't been there, my light would have continued on in a straight line like so, and instead it's been shifted some distance to the left. It's still coming out parallel, but just sort of at the wrong spot. And you've probably seen this sort of effect yourself. If you've ever like taken a glass of water, put a straw in that glass of water, and then if you look at the straw through the sides of the glass, what's going to happen is it looks like the straw is broken. And it will appear as if, you know, the glass or the location of the straw as it leaves the top of the water at the top of the glass is slightly off from where it is inside the glass. And what you're seeing is this same sort of directional shift from the light passing through the glass, as opposed to the light that doesn't pass through the glass and goes strictly from the straw to your eye. So yeah, that's pretty neat. But wait, what if I change the shape? Oops. What if I change the shape of my piece of glass? Here is a curvy piece of glass. And what's going to happen is if I strike this curvy piece of glass directly here in the middle, you know, we do have to deal with, like, how do I find the normal for a curve? And of course, the way you do the normal for a curve is that you imagine a tangent line at any given point. So at this point right here, my tangent line would be right there. And so the normal is perpendicular to that tangent line. So here, the light goes undeflected. However, if I take this piece of glass and I have it strike somewhere off to the edge, what's going to happen is the tangent line for that piece of glass at that location would be, so it'd be like this line, right? That's my tangent line, and here's my normal pointing to that. And you can see that what's going to happen is here I've got a non-zero angle of incidence, so I get a non-zero angle of refraction. And so the light tends to bend when it travels through the lens or the piece of glass going through the edge. So what will happen is, depending on where the light strikes, I might get bending in one direction or another, right? When the light hits the extreme edge of this piece of round glass, it's going to bend a lot. It's going to come out at a largely deflected angle from the original direction of travel. When it strikes the middle of the piece of glass, it doesn't bend at all. And when it strikes the bottom of the piece of glass, it bends, but it bends in the other direction. So why do I care about that? Well, one way to think about this, let's have a beam of light that's consisting of more than a single ray. Here I've got a bunch of rays. And of course, they're coming out of my laser, they're all coming parallel. Now, what's going to happen is each of those rays is going to strike the glass in a different location. They're all going to have slightly different angles of incidence, which means they're all going to have slightly different angles of refraction. But you'll notice that because the ones that hit exactly in the middle of the piece of glass don't bend at all, the ones that hit above bend downward, the ones that hit below bend upward, what occurs is that all these rays of light, regardless of where they struck the piece of glass, they end up converging at a single location. This is a lens, right? Lenses can often cause light rays to converge. So this is specifically what we're going to call a converging lens. Because, as the light strikes my converging lens, it tends to cause my light to converge to a single location. Now, you could also have a diverging lens. And this is an example of a diverging lens. Right. What's happening here is the exact opposite. Because now the beams of light end up refracting one direction on the inner edge. They refract a different direction on the outer edge. And when they come out the other side, my beams of light are all diverging, right? They're getting further apart rather than closer together. Again, if you wanted to explore how that works, here when I strike in the middle, my normal right here is straight up and down. So the angle of incidence is 0, and so it doesn't bend at all in the middle. But if I hit up here, you can see the angle of incidence for the inner edge is now this way, and when it bends, it's going to bend upward. Down here, it's going to bend still toward the normal, but now the normal is diagonally down. It's going to bend downward, and so that's why they're diverging when they go through. So, when you think about any time you deal with someone who wears glasses, or if you're using microscopes or telescopes, any sort of lens whatsoever, you're dealing with refraction. You're utilizing refraction over some curved surface to make the light curve in a useful way. And so Snell's law is going to give rise to the laws of optics that help us figure out what sort of lenses will get varying effects. So that's pretty easy. So when it comes to lenses, it turns out that the behavior of a lens is going to depend on a couple of things. It's going to depend on the index of refraction of the material that the lens is made out of. And it's also going to depend on the curvature of the lens itself. And unfortunately, this simulation doesn't allow me to change the curvature. And so when I pull this piece of glass out, all of my material converges at a particular spot, and I can't change that spot. However, if I go here, I have a bit more control over the varying parameters. So what I'm looking for here, Hopefully they're going to replace this one before the end of the year. Otherwise, next semester is going to suck. Because Flash is about to go away forever. So what I've got here is a lens, but I have a bit more control. I can change the index of refraction, and I'm going to turn on all the rays. So here's an object. And what I have is light leaving the tip of that pencil and traveling in a whole bunch of different directions. And let's do this. And so what's going to happen is, obviously, the light that leaves here, some of it travels out here and doesn't hit the lens at all. Some of these rays come out and they hit the lens and they're going to bend. And because this is a converging lens, they're going to tend to converge at a certain location. So what's going to happen is if I change the index of refraction and I make it larger, you'll notice they converge more quickly. If I make the index of refraction smaller, they converge less quickly. I can also change the radius of curvature. Here's a kind of a thin, not very curvy lens. Here's a much more curvy lens, and you can see that curvy lens causes my light to converge much, much, much more quickly. So what's going to happen is, for any converging lens, we're going to be able to characterize that lens in terms of how far away these light rays converge. And so the way we will do that, let me take this out to some particular value. And unfortunately, this sim doesn't do quite what I want for this. I'm going to have to draw it by freehand. So what's going to happen is, if I imagine a bunch of rays of light come in and hit this lens going parallel. So here I'm going to draw them. Here's a bunch of parallel rays of light. Imagine that they're straight. They're not. What's going to happen is those parallel rays of light will all tend to converge at a single spot, which is where this yellow X is. So that yellow X is called the focal point. And if I measure the distance from the lens to the focal point, we call that the focal length of my lens. You'll notice that they put a little yellow X on either side of the lens, and that's because, for most lenses, the focal length in the front would be the same as the focal length in the back. If I were to imagine a bunch of light coming in from this side and coming in parallel, that's a way better drawing. It would converge on that spot as well. So every lens has its own characteristic focal length. And the focal length depends on a combination of the curvature of the lens. So if I make the lens less curvy, the focal length will be further away. It also depends on the material that the lens is made out of, the refractive index of that material, because I can make the focal length larger or smaller by altering that as well. Now, what I can't do on this simulation is I can't show you the focal length for a diverging lens. This is the focal length for a converging lens. Let's go back over here. And ask ourselves, could I find the focal length for this guy here? And the answer is, yeah, you could, but you have to think about it a little differently. Because now what's going to happen is there is no spot where these light rays converge. They're never going to come together because they come in parallel and they come out getting further apart. However, if you were to take the diverging paths of the rays and trace them backwards, maybe I shouldn't use red for that. Let's use blue. So if I were to trace along this ray, what's happening is these rays are diverging as if they're coming from a single spot. So that would be the focal point of a diverging lens. And of course, the focal length would still be that same distance, the distance from the lens to the spot where the light appears to be diverging from. So if you just trace all the rays of light backwards, it appears they're all diverging from a single spot. That is the focal point of a diverging lens. Now, by convention, when we're talking about the focal lengths of lenses, the focal length of a converging lens will always be positive, and the focal length of a diverging lens will always be negative. So this distance here, I'd measure that distance, but I'd slap a minus sign on it to reflect the fact that the light doesn't really converge there. It just appears to diverge from that spot. So our sign convention is that diverging lenses have negative focal lengths, whereas converging lenses have positive focal lengths. Nifty. Let's go back to this guy over here. And what we're going to do for the next equally true for diverging lenses. So even though I can only view that converging lens in this demo, everything I'm about to say is going to work just as easily for a diverging lens. So what's going to happen is if I've got, like, say, this little lamp, and that lamp is shining a bunch of rays of light, what's going to happen is you'll notice these rays of light, they're not coming into the lens parallel, which is why they're converging, but they're not necessarily converging at the focal point. Remember, the focal point is just where parallel rays converge there. These light rays instead are converging at some other location. All right, if I move my lamp forward or backward, I can change the location of the point where those rays of light converge. So that location is going to be in something important. Now, right now I have the thing set on many rays, so I'm seeing like lots of rays, many of which don't ever even hit the lens to begin with. So these are obviously never going to converge because they're not traveling through the glass at all. So when we talk about lenses and try to analyze how lenses work, a lot of times we'll focus our attention on some very specific rays that are easy to predict their behavior. And so what we're going to do is we're going to reduce our total number of rays down to what we call our 3 principal rays. Right? And the 3 principal rays that travel through a lens are as follows. So imagine here's my lens, and here's my object. And right here, going right through the middle of the lens, this is what we call my optical axis. Right, that's just the line that goes through the center of the lens. Now, I'm going to have light leave my object and hit the lens from some location. And let's go from this guy's head. All right. And I'm going to track 3 principal rays. All right, the first ray is going to go from my point of interest to the lens parallel to the optical axis. So ray number 1 comes in and hits the lens traveling parallel to the optical axis. So it enters, right? It's going to enter parallel to the optical axis, but it's going to end up passing through the focal point on the other side. So if I'm doing the focal point of this lens, let's say the focal point of this lens is right here. And I'll go like that. So there's the focal point on either side. So this ray of light is going to come hit through here, but then when it hits the edge of the lens, it's going to bend quite drastically, and it's going to bend such that it travels through the focal point. Because remember, that's what the focal point was. Lines that come in parallel go through that spot. So he's coming in parallel, he's going to go through that spot. Now, the second principal ray that I'm going to pay attention to is going to hit the center of the lens. Now, remember we had that square up there and I had the line come in and hit, and it bent on the way in and it bent again on the way out, so it came out parallel. Well, if the lens isn't super thick, the amount of shifting you're going to get is not going to be very big. So the ones that hit the center of the lens are going to bend one way coming in, but because of symmetry, when they come out the other side, they're going to bend exactly the same amount on the way out, and they're going to come out undeflected. So ray number 2 is going to hit the middle of the lens and just go straight through. So far, so good. Now, the third principal ray is going to be the ray that goes through the focal point on this side. But it's going to end up being kind of the opposite situation from ray number 1. It's going to go through the focal point on this side. It's going to come out parallel on the other side. Just because of symmetry. So the third ray is going to go from this spot, hit the lens, come out parallel. And what's going to happen is my 3 rays of light are going to hit the lens at different locations, but all the rays of light will end up converging at that one spot. And so these 3 principal rays are super easy to sort of wrap our heads around. So even though we could always draw more rays, these are the ones that are easiest to deal with. And usually they tell us enough of the story that I don't need any more. So, going back here, you can see that right now I have my 3 principal rays, one coming in parallel, coming out through the focal point on the other side, one going undeflected through the center of the lens, the third going through the focal point on this side, coming out parallel. They all converge at a spot. And even if I had put in like more rays, you can see that they're still converging at the same location, even if they're hitting in other places in between. And so the point of convergence is the same. It's just way easier to find by doing the principal rays rather than some of the other rays. So, big deal. Why do I care? Well, the reason that I care is because if all the light from this one lamp is always converging at that spot, if I were to put a screen at that spot, it's going to seem as if the light from the lamp is shining right there. Put another way, what if I were to do this here's a pencil. And what's going to happen is I've got a bunch of light leaving the tip of the pencil in every which direction. However, light from the tip of that pencil tends to converge at that spot. Now, if I was then looking at the light coming from that spot, it's going to seem like I'm seeing light from the tip of the pencil. What if I were to put a second point on this pencil? Here's another point. Here's the eraser side of that pencil. Well, what's going to happen is I have light always leaving the eraser side of that pencil. And if I look at this one spot, I get light from the end of that pencil. What I'm going to see is the image of the pencil as if it exists at this location. So this is the image, and it's going to form at the location where all the rays converge on the other side. Now, what if I were standing right here? Or what if I put the screen back and I put the screen up here? Well, now what's going to happen is, like light from the blue lamp, it hits several different locations on the screen. Light from the red lamp hits several different locations on the screen. My image would be out of focus because, you know, one part of the object appears in several places on the screen. It's blurred out. If I'm going back to the pencil version, if I'm looking right here at this location right here, I would see the eraser at several different locations. It would be a somewhat blurry. Heck, if I look right here at this distance, I would see some light from the tip of the pencil and light from the eraser of the pencil arrive at the same location at that spot. I wouldn't be able to tell the difference between the eraser end and the tip end. It would be blurry and indistinct. But right here, light from one end of the pencil always arrives here. Light from the other end of the pencil always arrives here. I would have a clear, crisp, distinct image. And so by tracing these rays, we can figure out where those images will be clear and distinct. And so much of what we're going to do in this next chapter is figure out, how do I deal with the formation of images, and how do I learn how to manipulate the properties of my lens to get the sorts of images that I want. And you can see that what's going to happen is, you know, even right now, as I move my pencil closer to or further from the lens, you can see that the property of the image is going to change drastically. Like right now, I'm getting an image of the pencil, but notice the light from the eraser end is much further away from the light of the tip end. The image is enlarged. I'm seeing a magnified image. Notice as I change things like the radius of curvature, I'm also changing the magnification and the location of the lens. So by changing the properties of that lens, I can change how much they magnify or reduce my images. And so much of the topic of chapters 25 and 26 is going to be us figuring out how to manipulate these properties. And we're going to pick it up there and start that tomorrow. So just a reminder, that second exam was posted over the weekend. It is due, I believe, tonight at midnight. And so far, nobody's opened it yet. So make sure you take a crack at that. If timing is an issue, if you're not going to be able to get it in before tonight, let me know. I can always give you an extension. But we're going to have to get on that. And I know that at least one of you is going to have to do the same thing for this meeting, or this test they did for the last test, where you're going to have to set up a Zoom meeting or something for security purposes. So get with me with when you have time availability, and we'll try to make sure you can do that. So, all right. See you tomorrow. Study hard, do your homework.